Hello students, coming up with the next part of the numericals from the chapter work, energy and power. So we will be seeing today numericals from exercise 2b, which is based on different forms of energy, and among the different forms of energy for numericals you require potential energy and kinetic energy mainly, and then you will require the law of conservation of energy, where basically we will be seeing the conservation of mechanical energy. So before we start the numericals, let us take a look at all the formulas which you will require for this particular part. Starting with, first of all, we use tanks here for potential energy, and we have to deal with gravitational potential energy. So the formula comes as mgh. M is the mass, g is the acceleration due to gravity, and h is the height at which the object is placed. Then you have the second numerical where k stands for kinetic energy, and you have it as half mv square, where m is the mass of the body and v is the velocity at which the body is moving. Now, in kinetic energy, mass and velocity is related. In the same way you have studied last year that momentum also has relationship of mass and velocity. Momentum is the product of mass and velocity. So we connect here kinetic energy and momentum to get few formulas. Okay, so if I am going to write for momentum related to kinetic energy, so remember P stands here for momentum. The relationship comes as under root of 2 into mass of the body into the kinetic energy of the body. So this formula is very important to have, where there is a relationship between the momentum and the kinetic energy. From this we can get another formula to relate where kinetic energy is to be calculated. So P square by 2m. So from this formula only this comes, okay, just changing the side, just changing the subject, we get it like this. So these two formula are very important when we have to relate momentum and kinetic energy. Then I will come to the work energy theorem, okay. In this work energy theorem, what it says is that whatever is the work done will be equal to the change in the kinetic energy. So based on that, work done will be equal to the final kinetic energy minus the initial kinetic energy. So taking them separately, and then if we take common, we can write as work done is equals to half m, and in the bracket have it as v square minus u square. So if I multiply half m into v square, that gives me half mv square, that is the final kinetic energy, and half m into u square, half mu square, this is the initial kinetic energy. So we can use this by taking common, it will be easier to solve. Apart from these all, a very important thing to be remembered when we deal with law of conservation of mechanical energy is that whatever is the potential energy at a given height will be equal to the kinetic energy at the bottom part of the surface. Or if I am throwing an object upward, the initial kinetic energy will be equal to the potential energy at the highest point. A lot of time this relationship will be used. Okay, so we will be applying kinetic energy equal to potential energy. I hope all these formulas you have noted down. Okay, and we will apply them in doing the sums of exercise 2b and also of exercise 2c. So now let us begin with the numericals of the exercise 2b of work, energy and theorem. So the first numerical is two bodies of equal masses are placed at heights h and 2h. Find the ratio of their gravitational potential energy. So the masses are same, heights are different. We have to find the ratio of the gravitational potential energy. So we do it like this: u1 by u2 So we have to find the ratio of the two potential energies. So we will write the formula mgh. For h I will write h1. For mass it is same and g is same, so I will not use a subscript for it. And for the second one it is mgh2. For both the part, mg will get cancelled. You get h1 by h2. Height is here h, and the second one is 2h. So you get here as h and h cancelled 1 by 2. So we get u1 is to u2, writing in the ratio form, which is absolutely necessary. So the answer for the first one comes as 1 is to 2. Now let us move to the second numerical, which says find the gravitational potential energy of 1 kg mass kept at a height of 5 meter above the ground, and then calculate its kinetic energy when it falls and hits the ground. And g is given as 10 meter per second square. So first of all, let us calculate the value of gravitational potential energy. So second numerical, writing the formula mgh. The mass given in this is 1, g is 10, and the height given is 5 meter. So this is 5 meter. We get it as 50 joule is the potential energy. Then it is told calculate its kinetic energy when it falls to the ground. You know, I told whatever is the potential energy at a given height, when it falls and hits the ground, the entire potential energy gets converted to kinetic energy. So we can write here kinetic energy equals to potential energy, and here it becomes 50 joule. This is your answer for the second part. This was your answer for the first part. I hope these two simple numericals have been understood. Now let us see numerical number 3, which says a box of mass 300 kg has a gravitational potential energy stored in it equal to 29,400 joule. So you are given with the potential energy. Find the height of the box above the ground and take a look. G is 9.8 to be used. Okay, so a very direct sum. We just use the formula, substitute the value, and you can calculate the unknown thing. So because potential energy is given, so I will go to write U is equals to mgh. U is given to us as 29400. Mass is 300 kg. G value is told as 9.8 and then into h. So I can write h as this will 29400 will be divided by 300 into 9.8. So what I am doing is I am removing this decimal here, writing 98, and then I will use this 10 from here. So we get here 30 into 98. Okay, this 0 will get cancelled. Okay, if I take a look at 98 3 times, it will give you 294. So it is 3 times giving us 30, and then 30 divided by 3 will give you 10 meter. So this is the height at which the object is kept. That's your answer. So we are only asked to find the height above the ground. So this finishes number third one. Now let us take a look at the fourth numerical, which says a body of mass 10 kg falls from a height 20 meter to 8 meter. So initially it is at 20 meter, falls down to a height of 8 meter. So calculate the loss in potential energy of the body. If you know, if the height decreases, there will be a decrease in the potential energy. So we have to find that loss part only. And then we have to find total energy possessed by the body at any instant. At whatever height it is, what is the total energy possessed? So whenever we are asked to find the total energy possessed, I can simply take the energy what it was having at the initial position. That energy will remain throughout its journey. Although potential will decrease, but kinetic will increase. So you'll be using this and working out this numerical. Okay. So first of all, we will take that height what it has fallen through. Okay, so I am writing that height to be used in this loss of potential energy as 20 minus 8 equals to 12 meter. Then I will write loss in potential energy. So using the formula mgh, so m is given to us as 10, G here is given as 10, so that makes the calculation easier, and the height here to be used is 12 because we are finding loss in potential energy. So what is the height change is there, we have to write that, and so you get it as 1200 joule. So this is our first answer for the first part. I hope this is understood why we are taking 12, because we are asked to find the loss in potential energy. Then it is the total energy possessed by the body at any instant. So I write here total energy at any instant will be found out by finding the potential energy at the initial height, that is of 20 meter. So I write the formula first, mgh, mass is 10, g is 10, and now the height is 20. So that gives us 2000 joule. This is your answer for the second part. So do remember, whenever you are asked to find total energy at any instant, you can find the energy at any particular place, but because at the top only the involvement of potential energy is there, the body is not moving, so you can easily find it by using potential energy. Now let us proceed further to numerical 5. Okay, it says calculate the height through which a body of mass 0.5 kg is to be lifted if the energy spent in doing so is 1 joule, and we have to take g as 10 meter per second square. Again, a very simple numerical directly based to the formula. So number 5, it is the involvement of potential energy. So I am writing U equals to mgh, and the energy which is given to us is 1 joule. This is 1. Mass is 0.5 kg into G value is 10, and we have to calculate the height. So I can write here height is equals to 0.5 into 10 will give you 5. So 1 divided by 5 is 0.2 meter. This is your first answer. Okay, first means the fifth answer. So directly to the formula it was. Let us look at numerical number 6. It says a boy weighing 50 kgf climbs up from the first floor at a height 3 meter above the ground to the third floor at a height 9 meter above the ground. So from this first floor 3 meter to the third floor 9 meter, the gap is a distance of 6 meter. So we will have to take that, because what will be the increase in gravitational potential energy? Increase is asked, so it will be based on the increase on the height. So we'll be using that particular part. So first of all, I go to find here the increase in the height as 9 minus 3. The height as 9 minus 3 is equals to 6 meter. So I will write here increase in potential energy as mgh. So m here is 50 kgf is the weight. So you know, if weight is 50 kgf, then the mass is 50 kg. And then g value given to us is 10 here. So 10, and the height we got it as 6. So 6 5s are 30, and then 2 zeros. The potential energy increase is 3000 joule. This is the answer for this sixth numerical. So till now we are getting sums where it is directly use of the formulas. Okay. Now let us take a look at numerical number 7. A vessel containing 50 kg of water is placed at a height 15 meter above the ground, assuming the gravitational potential energy at ground to be 0. So the surface we are taking as 0. What will be the gravitational potential energy of the water in the vessel? G is 10 meter per second square. Again, a very direct formula sums. So we have to find the potential energy. So we write the potential energy formula mgh. So mass is given to us 50, G value here also told as 10, and the height is given as 15 meter. So 15, 5 into 15 is 75, and then the two zeros written, so we get it here as 7500 joule. Let us see numerical number 8. A man of mass 50 kg climbs up a ladder of height 15 meters. So he is climbing up, okay, going against gravity. Calculate the work done by the man. So we have to find the work done. He is going against gravity. So it is the work done due to the force of gravity. And the increase in the potential energy. See, whatever work he will do, the potential energy increase will be that much only. So whatever we get the result in the first one, the second one will also be the same result. And remember to see here G value is 9.8. Okay, so we begin the working of it. So it says above, we have to find the work done by the man. So here work done is due to the force of gravity. So we are going to use mgh. Okay, now mass is given as 50. G is given here 9.8 and H over here is 15 meter. So 50 into 99.8, if I use this 0 and remove the decimal, I get 98. And 98 into 5, if I multiply, I will get 490 multiplied with 15. So 15 zeros are 0. 15 multiplied with 9 will be 135. So 5, 13 is carry. 15 fours are 60. 60 and 13 will give you 73. So 7350 joule is the work done. This is the first part. Second part of it, it is asked increase in his potential energy. So as I told, that will be equal to work done. So I write here increase in potential energy will be equal to the work done. And so the same result comes 7350 joule. So this is your second part answer. This was your first part answer. I hope you have understood this concept of work done by the man in going up will be the same as the increase in potential energy. So now till now we were having a lot of very easy sums. Now little bit a better sum is there. Okay, so let us take a look at numerical number 9. A block A weighing 100 Newton is pulled up a slope of length 5 meter by means of a constant force F 100 Newton. So this is an inclined plane, and so this block at A is being pushed here like this, or pulled like this, a distance of 5 meter, okay, and then it is asking what is the work done by the force F in moving the block A 5 meter along the slope. So first we have to find the work done going like this. Second part, what is the increase in the potential energy of block A? Increase in potential energy. Potential energy deals with the height. So from the ground level going to this place, the height is 3 meters. So you have to consider then 3 meter, not 5 meter. And then it says, account for the difference in the work done by the force and the increase in potential energy of the block. We know that we have been relating that work done will be equal to the increase in potential energy, but you will not find the answer coming the same in both the part. Okay, here you will find work done to be coming more and the increase in potential energy will not be the same. So why is that difference? So that difference is because when we are taking this object along this slope, the two surfaces are touching each other, and you know that when an object moves over a surface, the force of friction comes. So because of the force of friction, there is a heat generated, and so you have to do work against that force of friction. That much of energy gets converted into heat energy over here. So we will see how much of that difference comes when we work it out. So let us do the working of it. So first of all, it is going along this inclined plane. So the force is there and the displacement is there. So work done, we will apply with what we had learned in the first part, F into S. So that is 100 into 5. So we get it as 500 joule as the work done in this part, the A part. Okay. Now in the second part, it is told what is the increase in the potential energy, okay, of block A. So B part, increase in potential energy, I will find it by mgh. Mass of the block is not given directly, but the weighing is given as 100 Newton. So that becomes the value of m into g. So I'll be writing here 100, and the height here is 3 meter. So 3, that gives me 300 joule. So you can see work done in taking along the inclined plane is 500 joule, but the increase in potential energy is not 500, it is only 300. So there is a difference, okay? So what is the difference? Is 500 minus 300 is 200 joule. Now we are not asked how much is the difference, we have to tell why that difference is there, okay? So this difference is there because you have to do the work against the force of friction, and which gets converted as heat energy, okay? This is due to the force of friction and that energy is in the form of heat energy. So I hope this concept, why they don't come same in this case, is understood and the reason is known. So let us proceed further. Now you will get few sums based on kinetic energy. So 10th one is of kinetic energy. See, it says find the kinetic energy of a body of mass 5 kg moving with a uniform velocity of 10 meter per second. Mass is given, velocity is given, a direct formula based sums. So we do it. So kinetic energy is half mv square. So half written, mass is given to us as 5 kg into velocity is 10 meter per second. It is a velocity square. So I do 10 into 10. So I can cancel this 5 times. And so 5 5s are 25. I get it as 250 joule. Okay, this is the answer of the 10th numerical, which was a direct numerical. So let us come to now question number 11. If the speed of a car is halved means whatever is the speed, gets divided by 2. How does its kinetic energy will change? So what happens to the kinetic energy, by how much it will change? So there is no change in the mass remains the same. So let us come to this numerical. So I will take the initial kinetic energy as directly the formula half mv square. I have denoted by I, telling that it is initial kinetic energy, and then the final kinetic energy I am writing as kf, or to say which is the new kinetic energy. What is happening? The speed is halved. So what do I do? Half and m written same. Now v is the velocity here, it is made half, and then this square is put. So v changed, we have changing accordingly as it is told. So I will get it here as half m into v square by 4. Okay, so I will be writing it as 1 by 4 into half mv square. Purposely I wrote it like this, so that half mv square was the value of initial kinetic energy. Okay, so I can write now that the final kinetic energy is 1 by 4 into the initial kinetic energy. So it means it has become 1/4 of it. The final kinetic energy is 1/4 of the initial kinetic energy. Okay, so I hope you have understood this, how to relate when one of the things in the physical quantity is changing. Now let us take a look at numerical number 12. Two bodies of equal masses, so masses are same, are moving with uniform velocities v and 2v. So the velocities are different. Find the ratio of their kinetic energy. So here it is to find the ratio. So very much similar sum, okay, but here it is in terms of ratio. So let us see how do we do this one. So ratio of the kinetic energy, first of all, I will write it in this way. Half m is not changing, so not giving a subscript. Okay, v1 square for the first one and half m v2 square for the second one. I can cancel this half and m, and now v1 was given as v and this is 2v. So V written, 2V written, both of them are having square. So I can give a common square to both of them. So now I can cancel that V part is cancelled. So I get 1 by 2 square, okay, which is 1 by 4. So I can write it now in the ratio form as 1 is to 4. So the ratio of the kinetic energy is 1 is to 4. Again I repeat, remember you are asked in form of ratio, you should leave your answer in ratio, not in the fraction form the way we calculated. It should be written in the ratio form. Now we begin with numerical 13. It says two bodies have masses in the ratio 5 is to 1. So ratio of their masses is 5 is to 1 and their kinetic energies are in the ratio 125 is to 9. You have to calculate the ratio of their velocity. So how we were dealing with the ratio sums, we will do in the same way, okay, and find the ratio of their velocity. So first of all, ratio of their masses are given. I will go to write them as m1 by m2 is equals to 5 by 1 and then ratio of the kinetic energy is given. So k1 by k2 is equals to 125 by 9. This I will write it, and now I will write the formula. K1 by k2 is equals to half m1 v square and half m2 v2 square. So here v1 and v2 has to be written because the velocities ratio we have to find. None of the physical quantities are remaining the same. So we have given subscript to all of them. So I can get rid of half and half here. K1 by K2 is given to me 125 by 9 and m1 by m2 is 5 by 1 and into I will write v1 by v2 because both of them are having a square. So given the square together. Now this 5 by 1 will come here. So 125 by 9 into 1 by 5 is equals to v1 by v2 whole square. So this will cancel it. 25. So I can write it now v1 by v2 is equals to root over 25 by 9, which you know root of 25 and 9 is 5 and 3. So I will get here 5 by 3. So I can write here v1 is to v2 is equals to 5 is to 3. So this is the way to relate and work out the sums when ratios are asked. Do not go to find their values separately and work it out. Okay, this way it is always better. Now to numerical number 14, which says a car is running at a speed of 15 km per hour while another similar car is moving at a speed of 45 km per hour. Find the ratio of their kinetic energy. So their masses are same because it is told similar car. Unit of speed is given as kilometer per hour. We will not go to change to meter per second. Reason is we are asked to find here the ratio. So they are in the same unit, let it be in kilometer per hour. Okay, so let us work it out. So we have to find the ratio of their kinetic energy. So I am writing K1 by K2 is equals to half m v1 square by half m v2 square. Now m is written same because similar car, so the mass is the same. This is cancelled. So v1 by v2 whole square. So v1 is 15. This is 45 whole square. So this will cancel 3 times. So 1 by 3 whole square will come as 1 by 9. So writing it in the ratio form as 1 is to 9. This is your answer of this 14th one. Okay. Let us now move to numerical number 15. A ball of mass 0.5 kg slows down from a speed of 10 meter per second to that of 6 meter per second. So there is a decrease in speed. Calculate the change in kinetic energy of the ball. So we have to find by how much the kinetic energy is changing. Okay, so we will be using kinetic energy formula. So initial and final we will be subtracting and getting it. Okay, so I will write here change in kinetic energy. So initial one and final one will be taking. Final one is having a speed of 6 meter per second. So I am writing here half m v square. So this is the final one, and the initial one I am now using it as half m. For velocity I am writing u square. So initial velocity is u. So you can see I can take half m common. So I get v square minus u square. So half m is here 0.5 kg. Final velocity which is there is 6 meter per second minus this one is 10 meter per second. Half into, 0.5 can be written as half. Okay, so I am writing half to make the calculation easier. And this is 36 minus 100. So 1 by 2 into 1 by 2 into this will give me minus 64. Okay, so this is 4 and 64 divided by 4 will give us 16. Okay, so this will give me minus 16 joule. Okay, now minus I am getting, that is showing that there is a decrease in kinetic energy. So I will write here decrease in kinetic energy equals to 16 joule. This is my answer. I hope you have understood how to find the change in kinetic energy. Now we proceed to numerical number 16. A cannonball of mass 500 gram. So remember that the unit is given in gram. We need to change it to kilogram. Is fired with a speed of 15 meter per second. So this is the speed given. You have to find its kinetic energy and then its momentum. So momentum here will be used, which you have learned the formula last year. P equals to mv, because mass and velocity is given. We can apply that. So we work it out. So first of all, this mass which is there is 500 gram. So I am writing here 500 by 1000. So this will change to kg and it will become half kg. Okay. So kinetic energy I need to find first. So half mv square. So half into mass is half kg and velocity is 15 meter per second. So 15 into 15. So that will give me 225 by 4. So which will give us, as all dividing it, you will get 56.25 joule. So this kinetic energy part we have got. This is the first part done. Okay. Now for the second part, it is told to find the momentum. M into V we can apply. So mass we have got it as 1 by 2 and velocity is 15. So you get it as 7.5 and then the unit of momentum is kg meter per second. Okay, so this gives you the second part of it. So we have got both the part of this numerical. The 16th one is done. Now let us take a look at the 17th one. A body of mass 10 kg is moving with a velocity of 20 meter per second. If the mass of the body is doubled, so whatever is the mass 10 kg will become 20 kg and the velocity is halved. So velocity from 20 it will become half, that is 10 meter per second. You are asked to find the initial kinetic energy and the final kinetic energy. So both the case we have to find the kinetic energy. A very direct to formula sums is there. So first of all, we will find the initial kinetic energy. Half mv square. So half into m is 10 and your v is 20. So 20 into 20. So you can calculate it out. Okay, this will cancel to give you 10. 10 tens are 100 and 102. 20 is there. So you get it as 2000 joule. Okay. Now coming to the next part, that is the second part, the final kinetic energy. For getting the final kinetic energy, we should know the new mass and the new velocity. If the mass of the body is doubled, so new mass becomes 10 into 2 equals to 20 kg, and new velocity, about velocity it is halved, so 20 by 2 will give us 10 meter per second. So we can go to find the final kinetic energy using the same formula. So I am not writing the formula again. Mass is not 20 and the velocity is 10, so 10 into 10. So this will give me 10, and all multiplied 10 here gives you 1000 joule. Okay, so you can see here the mass was doubled, velocity was halved. So one is doubled, the other is halved. Don't take it that the result will be the same, because here kinetic energy is depending upon the mass directly, but kinetic energy is depending upon the velocity, not directly, but directly with the square of the velocity. So that is why you can't take it that the result will remain the same. That you have to keep in mind. Such things, if you remember, you won't do if such numerical comes in MCQ. Now let us see question number 80. So little bit sums will be becoming now. More steps will be required. Little bit understanding level will increase. A truck weighing 1000 kg changes its speed from 36 km per hour to 72 km per hour in 2 minutes. So very important thing, that speed is given in kilometer per hour, we need to change it to meter per second. Okay, and calculate the work done by the engine. The speeds are given, mass is given, work done by the engine. So work done here, you have to remember, will be the change in kinetic energy, applying the work energy theorem. Okay, so that way you will get it, and then its power. Power will be the work done by the time taken. Okay, so we will be applying this and using it. So let us see how we will work it out. So first of all, I will be writing here work done is equal to the change in kinetic energy according to the work energy theorem. So I will write that relationship directly. So I am finding the work done here. So half into mass is 1000, and the velocity which is there, 36 km per hour and 72 km per hour, needs to be converted. Okay, so if I find here 36 into 5 by 18, okay, so we know that we have to convert kilometer per hour into meter per second. We need to multiply it with 5 by 18. So this will give me 18 twos, so I will get it as 10 meter per second. Okay, and same way 72, if I go to convert into 5 by 18, so 18 4 is 72, I will get as 20 meter per second. So this is my u value, this is my v value. So I will be putting the values here, 20 square and 10 square. So half into 1000, now we are getting 20 square minus 10 square, so I can apply a square minus b square formula, a plus b, a minus b. So 20 plus 10 will give me 30, and 20 minus 10 will give me 10. Now I can cancel this 2 with this 30, 15. So I get here 153010, 4 zeros altogether. This much joule is my work done. So this we have got work done by applying the work energy theorem. Now it is told to find the power. So we know that power formula is work done by time. I am going to write here 15, then 4 zeros divided by the time is 2 minutes. So I will do by 60. Okay, dividing this 0. Let me cancel with 2 first. So 2 sevens are 14, 1 left. 2 fives are 10, and then 2 zeros, and then with 6 if I reduce it. Okay, so 6 ones are 6, I am left with 1, 15, 6 twos are 12, left with 3, 30, 6 fives are 30, and then 0. So I get it as 1250 watt. So this is your answer for finding the power part. I hope you have understood how to apply this work energy theorem. Second part was easy. We have done it in the previous part also. So now let us come to question number 19, which goes like this. A body of mass 60 kg has a momentum of 3000 kg meter per second. So you are given with mass and momentum. Calculate the kinetic energy. You are asked to find the kinetic energy. Remember, velocity is not given. Okay, and you are asked to find that velocity, or to say the speed of the body. So you know we had the formula connecting kinetic energy and momentum. So you have to apply that formula to do this sum. So we write the formula because we are asked to find kinetic energy. To find kinetic energy when momentum is given, the formula is K is equals to P square by 2M. So P is 3000 given here. Okay, so 3000 square is there, so into 3000 by 2 into mass is given as 60. So I go to reduce here, 0 cancel, with 6 I reduce, 6 5s are 30, then with 2 25. So you get 3 into 25 as 75, and then 3 zeros. This much joule is the kinetic energy. So first time you are getting a numerical where you are using the relationship connecting kinetic energy and momentum. Now next they have asked to find the speed of the body. Okay, let me write this as the answer. So this was the first part. Second part, speed, I can use this formula. Momentum is equal to mass into velocity. Momentum is 3000. Mass is 60 and velocity we have to find. So V will be equals to 3000 by 60. So this is cancelled. So if I divide 6 5s are 30, then 0 is left. I get it as 50 meter per second. So second part was an easy one, a very small formula and a direct to formula sum. So we move on to the numerical number 20. Take a look at this question. It says, how much work is needed to be done on a ball of mass 50 gram? Okay, the mass is 50 gram to give it a momentum of 5 kg meter per second. We are given the mass and the momentum and we have to calculate the work done. Remember, the work done here will be equal to the kinetic energy which the body or the ball will be having. So we go to solve it in this way, that the work done will be equal to the kinetic energy, and kinetic energy in case of momentum, you know we have a relationship P square by 2M. So here the momentum is given to us as 5. So 5 into 5. 2 into mass is given to us 50 gram. So that has to be converted to kilogram. So we write here 50 by 1000. That 1000 I can write it in the numerator. Now let us simplify it out. So this is cancelled. If I cancel here 20 and then I get a 10, so I can write it as 250 joule. So the work done we are getting here as 250 joule. Okay, so we have applied work done equal to kinetic energy, and kinetic energy formula based on momentum is used. So now coming to numerical number 21, the question is like this: how much energy is gained by a box of mass 20 kg when a man, so there is a box of mass 20 kg, and in different condition we will have to find the work done. That is, carrying the box waits for 5 minutes for a bus. So how much energy is he going to, is being gained if he is just waiting, standing there with the box, no movement, okay, no lifting, nothing is being done, just he is holding it. And then in the B case, runs carrying the box with a speed of 3 meter per second to catch the bus. Now he runs means motion is there, so kinetic energy will be used, and raises the box by 0.5 meter in order to place it inside the bus. Now he is lifting it up. So lifting it up, he is doing work done against the force of gravity, means potential energy will be used. So let us work it out one by one. So going by carrying the box and waits for 5 minutes, waiting, no lifting, no movement. So he will be doing no work, so energy will be 0. So how much of energy is gained? Energy gained will be equals to 0 joule, because again I repeat, no movement, no lifting it up, so neither kinetic nor potential energy comes. So this is the A part. Now let us come to the B part. B part of it says that runs carrying the box with a speed of 3 meter per second. So kinetic energy will be used here. So I will write kinetic energy half mv square, so half into the mass is 20 kg and the velocity is 3 meter per second, so 3 into 3, this cancels it, 10, 3 3s are 9, we get it as 90 joules. So when he is running with it, he is gaining energy of 90 joule. And in the third case, in the C part, raises the box by 0.5 meter. So if he is raising it, potential energy will be used. So U equals to mgh. So mass is 20, g it was given as 10, and then the height which is there is 0.5 meter. So 10 and 0.5 will become 5, 520 is 100. So you get it as 100 joule as the answer for the C part. I hope you have understood in different scenario where which formula to apply and do it. Now we come to numerical number 22. Follow the question, little bit different type of numerical this is. A bullet of mass 50 gram is moving with a velocity of 500 meter per second. It penetrates 10 centimeter into a still target. So a target is still, penetrates and comes to rest. So final velocity is 0. Calculate the kinetic energy possessed by the bullet. So when it is moving, what is the kinetic energy? So we will apply kinetic energy formula half mv square and get it, because we know all the required quantities. Then the average retarding force offered by the target. So the target brought that bullet into rest, so it is applying a retarding force. So we are asked to find that retarding force. Remember, whatever the kinetic energy the bullet was having, the same work has to be done to stop it because it comes to rest. So we will apply that whatever kinetic energy is there, that much of the work has to be done by that target to bring it to rest. So then we will apply work done formula, and that force which is there will become the retarding force, because the displacement is given to us as 10 centimeter. So let us see the solution. So first of all, we are asked to find the kinetic energy possessed by the bullet. So we go to write kinetic energy equals to half mv square. So half into the mass which is there is 50 gram. So changing it into kilogram by 1000, and then velocity is given as 500. So 500 into 500, because v square is there, so we can reduce it. It will go 2 times here. Okay, I can cancel this 25 here, and I can cancel this as 250. So we have a 25 and a 25, you know, is 625, and then a 0. So kinetic energy possessed by it is 6250 joule. That is your answer for the A part. So we were doing the A part, this is the answer for it. Now the next part, it is told what is the average retarding force offered by the target. So as I said, this is the kinetic energy the body is having. If it is brought to rest, it has to do this much of work done to bring it into rest. So I will write here, work done is equals to F into S. In place of work done, I will write 6250. This force is the retarding force. So I will just here write now F, and the displacement which is there is 10 centimeter. I need to do the conversion here. So 10 by 100. 1 0 is cancelled. This will go and multiply here. This is the retarding force. So I am writing here currently retarding force. So that will be 6250 into 10. So you get 62500 Newton. So this much is the retarding force has to be applied. I hope you have understood this type of numerical here. So coming to the last numerical of this part, okay, of the second part of work, energy and power, and it's a very, very good numerical. A spring is kept compressed by a small trolley of mass 0.5 kg lying on a smooth horizontal surface in the adjacent figure 2.16. So what it says till here should be understood. This is a trolley and this is a spring has been kept compressed by this trolley. Okay, and the mass of the trolley is 0.5 kg. It says when the trolley is released, now the trolley is not binded by any force, it is just released. It is found to move at a speed of 2 meter per second. So because once it is released, it begins to move because there was kinetic energy, potential energy stored over here. It moves with a velocity 2 meter per second. We are asked what potential energy did the spring possess when compressed. So first of all, know it, here the potential energy is elastic potential energy. The potential energy when the spring shape is changed. Okay, so it is compressed and kept, it is having some potential energy. And when it is released, it moves with a velocity 2 meter per second. So it gets kinetic energy. So here also, the potential energy of the compressed spring will be equal to the kinetic energy. So you'll be applying that concept only over here. So we go to write first the potential energy is equals to the kinetic energy, and then we write here half m v square, half into mass is 0.5 and the velocity is 2 meter per second. So 2 into 2, we cancel it out. 0.5 into 2, you know, will be 1 joule. So the potential energy possessed by this compressed spring is 1 joule. I hope you have understood how to relate elastic potential energy also with kinetic energy. We come to the end of this part. Okay, we will be doing the next part, that is the third part of this, that is the 2C exercise. Also will be doing it. If you have understood this numericals which we have done, do remember to like the video, subscribe to my channel, and please do comment also. What is your requirement, what new things you want, I will try to do it on that. Thank you for watching.